In the question, in the circuit shown below, switch SW is in position 1 for a long time and brought to the position 2 at time t equal to 0 and determine the circuit current. In this case, we have, while connected to the position 1, there was a source connected to our circuit. So due to that, definitely the circuit reaches a steady state. Okay, while the circuit reaches steady state, the inductor will act as a short circuit. As we discussed in the previous part, the inductor will act as a short circuit when the circuit reaches a steady state. So according to the question, the switch is in the position 1 for a long time and brought to position 2 at time t equal to 0. So I can consider from time t equal to minus infinity to 0 minus, the circuit was connected, the switch was connected to position 1. So the circuit looked like this. So definitely the circuit reaches a steady state, so I can replace this inductor with a short circuit. I can replace this inductor with a short circuit. So circuit will look like this. We have 50 volt source and a resistance, and the inductor is replaced with the short. So in order to find the initial current, just I of 0 minus will be equal to 50 by 5, will get 10 amperes. So that is my initial current, and inductor will not allow sudden change in current. Inductor will not allow sudden change in current. I of 0 minus, I of 0 minus will be equal to I of 0 will be equal to I of 0 plus, which is equal to 10 amperes. At time t equal to 0, what is happening? The switch is changed to position 2. The switch is connected to the position 2. We have a 10 volt source instead of 5 volt source connected to it, and we have 5 ohms and an inductor 2 Henry. So I'm going to apply KVL for this. I'm going to get 5 I of t plus 2 dI of t by dt. Okay, voltage across the inductor is L dI of t by dt. So instead of L, I can write 2 dI of t by dt minus 10 equal to 0. Take Laplace transform. I of t can be written as I of s. So 5 I of s plus 2 s I of s minus I of 0. So what is the initial current we have? 10. So I can replace this I of 0 with 10, which is equal to, so this 10 can be written as 10 by s. 10 can be written as, so while taking Laplace transform, I of s can be written as, I of t can be written as I of s. 2 dI of t by dt can be written as s I of s minus I of 0, and 10 can be written as 10 by s. I can replace this I of 0 with the initial current which we calculated in the previous step, which is 10 amperes. I of 0 equal to 10. So 5 I of s plus 2 s I of s minus 2 times 10 equal to 10 by s. 2 times 10 equal to 10 by s. So I of s, I can take I of s outside. So 5 plus 2 s equal to 10 by s plus 20. So I of s equal to 10 plus, I am taking LCM here, 10 plus 20 s by s multiplied by 1 by 5 plus 2 s. I am going to take 2 outside in order to write in the form of s plus a. So 10 plus 20 s by s multiplied by 1 by 2 times s plus 5 by 2. So I can cancel. So I can take 2 outside and I can cancel the 2. 5 plus 10s by s multiplied by s plus 5 by 2. By using partial fraction, I can write 5 plus 10s by s into s plus 5 by 2 equal to a by s plus b by s plus 5 by 2. So take LCM here, a multiplied by s plus 5 by 2 plus bs by s times s plus 5 by 2. I can cancel these two denominators. So and I can initially apply s is equal to 0 and I can find a. So I'll get a is 2 and substitute s is equal to minus 5 by 2, and I'm going to is equal to minus 5 by 2, and I'm going to find the value of b, which will get 8. Substitute this in that. Instead of b I'm going to substitute 2, instead of b I'm going to substitute 8. So we're going to get I of s equal to 2 by s plus 8 by s plus 2.5. While taking inverse Laplace transform, I'm going to get 2 by s. If I take inverse Laplace, I'm going to get 2. 8 by s plus 2.5, 8 multiplied by e power minus 2.5 t, which is equal to, I can take 2 outside, 1 plus 4 e power minus 2.5 t amperes. Next problem is, in the circuit, in the RL circuit shown in figure below, switch is closer to position 1 at t equal to 0. Then at t equal to 0.24 second, the switch is moved to position 2. Determine the response I of t and sketch the response. Also determine the time at which I of t is 0. Here they are given the switch is closed at time t equal to 0, okay, to the position 1. Okay, and at t equal to 0.24 the switch is moved again. They didn't mention the steady state at any time. Okay, they didn't mention that. Okay, so initially I am going to assume that the switch is connected to position 1. So how the circuit look like? At time t equal to 0, we have a 10 volt source, 10 ohms and 1.2 Henry. This was our circuit at t equal to 0. So before t equal to 0, the switch was open, so the initial condition is 0 here. So there is no initial current available. So I have 0 equal to 0. I am going to apply KVL. So we get minus 10. Sorry, it is plus 10 I of t plus 1.2 times di of t by dt equal to 0. Here 10 I of t plus 1.2 di of t by dt equal to minus 10. Okay. We have 10 I of t plus 1.2 di of t by dt equal to minus 10. Take Laplace transform. I of t can be written as I of s. 1.2 can be written as 1.2. di of t by dt should be written as s I of s minus I of 0. So we consider there is no initial current. So I of 0 will be 0 here in this case, which is equal to minus 10 becomes 10 minus 10 by s. So I am rearranging this equation. So I can write as 10 I of s plus 1.2 s I of s equal to minus 10 by s. I can take I of s outside. 10 plus 1.2 s equal to minus 10 by s. So we have I of s multiplied by 10 plus 1.2 s equal to minus 10 by s. So this can be written as minus 10 by 10 plus 1.2 s, which is equal to minus 10 by 1. I am going to take this 1.2 outside so that I can write in s plus a form. So minus 10 by 1.2 s multiplied by s plus 10 by 1.2. So which can be written as minus 8.33 by s multiplied by s plus 10 by 1.22. By partial fraction I can write minus 8.33 by s multiplied by s plus 8.33 equal to a by s plus b by s plus 8.33. So I can take LCM here so that I can cancel the denominator. I will get minus 8.33 equal to a s plus 8.33 plus bs. The s value can be 0 and s value can be minus 8.33 in order to get a and b. Which is substitute s is equal to 0. I will be getting a equal to minus 1. Next substitute x is equal to minus 8.33. So minus 8.33 equal to b times minus 8.33. b will be equal to 1. So I of s equal to minus 1 by s plus 1 by s plus 8.33. So I take inverse Laplace transform. So I will get minus 1 plus 1 by s become 1. 1 by s plus 8.3 become e power minus 8.33 t amperes. At t equal to 0.24, according to the question, we need to find what is the current at t equal to 0.24. We are doing the switching at t equal to 0.24. So inductor does not allow the sudden change in current, so I can find out the current flowing in the circuit at 0.24. So I just substitute, instead of t I'm going to substitute 0.24, I'm going to get minus 0.8645 amperes. Okay, next case is the switch is moved to position 2 at t equal to 0.24. So it is moved to position 2. The circuit look like this. We have 2 volt source, 20 ohm resistor and 1.2 Henry. Apply KVL for this at time t equal to 0.24 seconds. Minus 2 plus 20 I of t plus 1.2 dI of t by dt equal to 0. 20 I of t plus 1.2 dI of dt equal to 2. I can take it to the other side. So take Laplace transform. So I of t can be written as I of s. 1.2 dI of t by dt can be written as 1.2 multiplied by s I of s minus I of 0.24. Why I written 0.24 here? Because the switching happened at 0.24 seconds. So initial current at 0.24 seconds I need to know, which is equal to 2 can be written as 2 by s. Okay, substitute the value of I is 0.24 in the equation, so that I can write 20 I of s plus 1.2 s I of s minus 1.2 times 0.8624 equal to 2 by s. This can be written as 2 by s minus 1.0374. So I of s can be written as 2 minus 1.0374 multiplied by s. I just take the LCM divided by s multiplied by 1 by 20 plus 1.2 s. Again rearranging, I will get 2 minus 1.0374 s by s multiplied by, I am going to take this 1.2 outside so that I can write s plus a form, s plus 20 by 1.2. So the equation can be written as, I am going to divide this 2 with 1.2, we will get 1.667, 1.0374 with 1.2, I am going to get 0.8624 divided by s multiplied by s plus 16.667. By partial fraction, I can write this equation equal to a by s plus b by s plus 16.667. b by 16.s plus 16.667. Take LCM, cancel the denominators on the other side. So I will get equation a multiplied by s plus 16.667 plus bs equal to 1.667 minus 0.8624s. There are two possibilities for s. S is equal to 0 and s is equal to minus 16.667. If I substitute s is equal to 0, a will be 0.1. If I substitute s is equal to minus 16.667, your b will be minus 0.96. Substitute in the equation, so we will get I of s equal to 0.1 by s minus 0.96 by s plus 16.667. Take inverse Laplace transform. 0.1 by s can be written as 0.1. 0.96 should be written as 0.96. S1 by s plus a can be written as e power minus 80 e power minus 16.667 t ampere. Now I need to find out at what time your current becomes 0. At what time the current becomes 0. So I can write the current equation which is equal to 0 so that I can find out the unknown value t. So 0.1 equal to 0.96 e power minus 16.667 t. So if I reduce this, you get 0.1041 equal to e power minus 16.667 t. So how can I cancel this e? I need to take ln on both sides. Ln on both sides. So if I take ln of 0.1041, I will get minus 2.2617 equal to minus 16.667 t. So ln e power minus 16.667 can be written as minus 16.667 t. So I will get time equal to 0.1357.